Okay, good.
The anticipation has been building. So. All right. So our second talk of the morning is from Christine Shoemaker, and she's formerly from Cornell. We had a nice talk the other day. And she's going to talk to us about, well, it's a very long title, so it has to do with optimization, uncertainty quantification, and deterministic surrogates.
Okay, thank you very much. Well, I really enjoyed this conference a lot, and I've learned a lot while I was here. So as a result, I changed my talk to kind of incorporate some of what I learned. But in the middle of it, my computer's sort of been dying. So I hope if you see some sort of strange slides, I didn't quite catch that correction. Yes, I am going to talk about, my focus is on simulation models. So I work a lot with applied problems. There's usually a simulation model that is not only nonlinear but typically multimodal, and so doing anything with it, optimizing it or doing uncertainty analysis is challenging because of that. In addition, it's also probably computationally expensive. Some of the models I work with actually take as much as 4 hours for one simulation analysis. So you really have to have a method that can come up with answers relatively efficiently. So this is the work I'm going to talk about. Some of it goes back quite a ways, and some of it is more recent. It includes a number of other people. And I also wanted to use this to make a commercial. There is a mathematical programming conference in Bordeaux, France this summer in early July, and there will be some sessions on surrogate optimization. My department has got some faculty openings, and we're particularly having trouble finding good people in deep learning. So if you know of anybody who might be interested, please talk to me or write me. And I personally have some postdoc openings. Okay, so this slide right here is also the slide I'm going to show at the end of the talk, because there's a couple of points, big points I want to make. One is that using optimization search can greatly increase the efficiency of surrogate-based uncertainty quantification. So I know that many of you do surrogate-based uncertainty quantification, and you have certain sampling methods. I'm suggesting that you incorporate optimization in an early stage of the sampling procedure. Secondly, is that we have been using deterministic radial basis functions. And we find that they're usually more efficient than Gaussian process plus expected improvement models for global optimization in higher dimensions, meaning 10 or higher, and they work equally well in lower dimensions. So I'll show you some of the results that we have for that, and I very much appreciate some feedback on this concept. And thirdly, that I'm going to use some examples that are real examples based on real data to demonstrate that global optimization and UQ can be used with deterministic surrogate can efficiently incorporate very complex and computationally expensive simulation models of real and complex applications. So just a simple statement, what we're trying to do with, so I'm going to talk first about optimization, because the optimization I also want to use in the uncertainty quantification, so I will talk first about global optimization with surrogates. So our goal is to find the minimum of some function over a domain D, and we have some upper limit on the number of evaluations, because these are expensive functions, you can't run them forever. And what we'd like is to be able to get a good answer with a small number of evaluations. In this context of this talk, mostly this F will be a measure of the error between model and prediction and observation. So we do a lot of work with the complex simulation model that has model parameters, and then we're trying to pick those parameters so that the model, the difference between the model predictions and the observed data is minimized according to some sort of a goodness of fit measure. And then in that case, in that kind of application, X is a parameter value. And then just to stress that I'm talking about problems that are in general multimodal. In other words, you may not know that they're multimodal, but you can't rule that out, because if you have a nice convex function, or of course a linear function, there are absolutely fantastic methods for doing optimization. But the problem is, how do you deal with these real problems that are like this? And that does arise in simulation model that's nonlinear, especially when you have several nonlinear processes sort of interacting. It can give you a higher order, equivalent of a higher order polynomial, which will be multimodal. This is an example from a very widely used model called SWATs, watershed models. Some of the applications I'll talk about later use this model, and these are just some simulations that were done varying one parameter at a time, holding the rest of them constant, and you can see what kind of a rough surface you get. So these aren't, when I was a graduate student, they taught us about Cantor sets, and they sort of like creating these really difficult things, these sort of pathological examples. But this is not some sort of pathological example. This is a real, something that really does occur. It's important in terms of providing you with water and clean water and all that sort of thing. And just in general, what we're talking about is we have, say, a simulation model, probably computationally expensive, could be partial differential equations being solved by some sort of finite element method, or could be like the slide I just showed, which is more of a difference equation kind of model, time stepping. And then we have an objective function. So the objective function depends on the output from the simulation. And for example, omega could be sum of squared errors or some other goodness of fit that looks at the difference between the output from g of x and the data. One of the examples I'm going to talk about is actually is more of a management problem. You're trying to reduce the amount of pollution, and so that in that case, omega measures the amount of pollution left after some actions that you've taken. So then when we talk about f, then we're trying to minimize this function, which is omega of g of x. And each evaluation of g of x is expensive, possibly hours, and so that means each evaluation of f of x is expensive. And we build our response surface is built on f of x. So for example, if we're doing, that means f of x is a scalar. So g of x may have many outputs, but f of x is a scalar. And so usually nonlinear simulations do produce a global optimization problem. So again, you have this problem to deal with. So the surrogate that we use, there's a lot of interest here in surrogates. We use what's called a radial basis function. The trouble is that these terms are used in different ways. So I'm going to describe what we mean by it, but it was one of the first places it was used in optimization was in this paper by a student of Powell's, who's very well known in nonlinear optimization, and it was from Powell's interest in radial basis functions that it's encouraged us to use that approach. So this is the radial basis, just as a real valued function, and we're using here the radial basis as interpolating functions. In other words, the surrogate we build actually goes through this is the data points that we have, and this is the surrogate approximation at those where the xi are the points where you have measurements. So our overall then RBF surrogate is then the sum of all these radial basis functions, and it's going through these points xi. These are measured values of the objective of the decision variable. And then there's also a polynomial, often called in this case, a linear polynomial called which is referred to as a linear tail. And then the lambda i's are going to be fit in order to make this polynomial go through your points. X or I are the points that we've already evaluated. So when you're doing these expensive evaluations, these previously evaluations of the expensive simulation model are really a treasure. You spent hours maybe getting those points. So that's why you're using them so carefully to incorporate them into the surface. These models are called radial basis functions because this is a linear combination of shifts of the function that is constant on spheres. So you can have different types of radial basis functions. We've had the most success with cubic results. Thin plate spline is also pretty good. Noting Gaussians here because it draws more comparison to, say, a Gaussian process model, and so we will be talking about this one as well. We do not find that this one works nearly as well as this one here, and you can read about this in many places, but this happens to be a paper that I wrote with my student Stefan Wild, who many of you know. Just to be careful, because I've been very confused by what people have been said since here is that the surrogate that we are using is not what you would call a Gaussian process with an RBF kernel. The model we use is the mean of the Gaussian process model with a cubic kernel, plus a linear polynomial tail. Our RBF is deterministic because it does not attempt to estimate uncertainty or covariance. So we're just using the mean of that. And so then in order to what we have to do is estimate the lambdas, and these are the coefficients of the polynomial, and so you have to solve this linear system with this definition of the terms. So these are things to be estimated, and these are to be estimated, and then this is the given data, and this is the value of the function at those data points. So these are all previously evaluated points, and these are the values that you got when you did those expensive simulations. The way we do this is similar to what is done with GPs. You originally use some kind of an initial search method, like in Latin hypercube, to search on the space to get some initial points to get your first surrogate, and then you start continuing to update that surrogate. I just want to insert here that we did the algorithm I'm describing was published. The basic algorithm was published in 2007. We've made many improvements since then, but it does converge almost surely. So this is this has some theory behind this particular approach. So then what you're doing is, as you've done a couple of evaluations, say if you've chosen to evaluate it at this point, remembering that each of these points is maybe took an hour to get those values, then the red curve is showing you the spline that goes through those. And this is actually based using a radial basis function. And then we pick a new point, just like with a GP expected improvement. You try to maximize the expected improvement. You picked a new point for evaluation, maybe over here. Then you add that to the curve, and maybe its value comes here, and then you're going to update the curve to fit it, as you would with the Gaussian process model. Okay, so here's a simulation of what we're doing. So this is the Ackley function, which is the blue line here. So it's a rough, difficult function to minimize. You can see that the solution is down here. But of course, when you're trying to search on it, you don't know the blue curve. All you know is the values of the black points, which are the previously evaluated points. And in this animation, the red square is showing you the most recent value of the evaluation, and you see it turns to a black dot. And then what you'll also notice is that it may get some points that are pretty far down, like here, it got a really great solution, but now it's going to jump back up again. And that's what you have to do with global optimization, because you can never assume that if you're at a local minimum, you don't know that it's the global minimum. And so you've got to constantly continue to explore. So here's it's the same thing, only just a little bit blown up. So the green here is a surrogate based on the previously evaluated points, and as you can see, that's getting updated as you go. The method that we're talking about is designed for difficult problems with multiple dimensions. We've gone up to 200 dimensions. I think that's really a stretch. It doesn't mean we got the right answer, but it means we got a better answer than anybody else for that many evaluations. And with high dimensions, we observe that our stochastic method is much more efficient than EGO. And it's also as good or better than EGO at lower dimensions. And EGO meaning Gaussian process plus expected improvement. This is an example on this is a very complicated groundwater model. The original model took a couple hours to run, and it has a lot of nonlinear terms in it. One of the things you're trying to do is estimate a parameter that's in the denominator of a coefficient of a term in a differential equation, so you can imagine that that's quite difficult. And these are compared to different methods. One of which is, for example, a linear, derivative-based solver, and a genetic algorithm, for example, and this does much better. This is ours, and this is everything's done with multiple trials, because these are stochastic algorithms, so you have to do it with multiple trials. But this converges very quickly. So that's just to show a success on one very difficult simulation model. We have a a package called PySot. That's an open source software for surrogate optimization, and it's with computer scientist David Bindel at Ericsson, who was my former student, now is Bindel's student. They're at Cornell. And the toolbox implements all the 5 steps of a surrogate search that we discussed. The language is in Python. It's been downloaded over 18,000 times. And it enables one to implement most of the algorithms I've developed over the last 12 years or so. So this is, if you wanted to do the kind of things we're doing here, this is an open source software package that's, Bindel is, I'm a terrible programmer, but Bindel's a wonderful programmer, so it's really beautifully done. So this is, I know there's a lot of interest in deep learning, so I thought I'd use a deep learning example of what we've been trying to do. So this was done with 2 people in electrical engineering who know about, the question?
What do you prefer, at the end or we do now? Just because you're going to change topic and I have a question about what you just showed, you prefer at the end or shall we ask now?
I have a lot of slides, but you're going to leave or something? Is that is that the plan? I guess if it's something you don't understand, I'd rather you ask now. Okay. If it's something is more of a discussion topic, I'd rather do it later.
Okay, I understand. So when you choose your radial basis function, every time you have a new point, you need to generate a new radial basis function. You use always the same kind of radial basis function, or you are changing like the smoothness of the radial basis?
We use the same. I mean, I guess you could think of changing it, for example, but we have always used the same, and pretty much we stuck with cubic, just because it was not that we have a theoretical reason for why it's better, but it has and not only us, but other people. We've seen other people in papers, whereas a Gaussian doesn't work well at all. Okay, yeah?
You haven't said how you choose a new point.
I'm going to tell you how we choose a new point. Okay, but here's a machine learning example. So these guys are, and I'm not a deep learning expert, but these 2 guys are, and this is based on image analysis. But what we were doing, and Jim wrote the paper, was actually mostly about the optimization algorithm, was that we introduced this new application algorithm that worked very well, and we were looking at a problem that had it was a deep learning problem, so it had a high number of dimensions. As I said, if you're a low number of dimensions, there's not that much difference between our method and the Gaussian process expected improvement approach. So when you do a deep learning problem, there's what you're trying to solve is this problem right here, and which is you have hyperparameters, and then you also have the weights in the neural net. So this part was done by our PySot. So this is our expensive evaluation, was finding out what should be the hyperparameter values. But in order to evaluate the objective function, then for a particular set of values for that hyperparameter, then you solve the neural net. And this takes a lot of time, so this ends up being an expensive operation. And this solution was done using just traditional stochastic gradient methods. Okay, so here's the problem that we did. So we're doing the surrogate optimizer. The algorithm we use for this, which includes integer variables, we called Horde. And then, so this is the upper level, and then this is the level with the neural net. And these are the results that we got. So these are, first off, the lowest curve is best. You're looking at number of evaluations, so this is a measure of the computational effort. And you could cut it off at any point, right? You don't have to run, we did 200 evaluations, but you'd probably like to get an answer sooner. And then this is the value of it, which is the best validation error. So lowest is the best, so the low curve is the best curve. So this right here is a Gaussian process expected improvement curve. And this is this is a leading method. Actually, I guess the second slide shows that. So this one right here is a leading method for using Gaussian process with expected improvement on this problem. Now this problem has 19 decision variables, so that's what's what's making it difficult for it. If this method works quite well if you've got 4 decision variables or something like that. It's because that it's so many decision variables that it's not doing very well. And this is our method that would be comparable to that, this green one. In both cases, they're starting without any sort of intelligent starting point. This particular existing algorithm, which is not ours, starts with an intelligent starting point, and we can also do that with our algorithm. It's very easy to incorporate an intelligent starting point, and so that's what our red one is here. So you can compare our algorithm to the purple algorithm, because they both had intelligent starting points, and if you look, it's like 200 evaluations for the purple one to get this answer over here. We got that same answer in only 54 evaluations. So it's a speed up of 3.7 times faster to get the same answer. Question?
Can I just ask, with the Gaussian process you're fitting, does that have a constant prior mean? I'm just asking.
I don't even know, and I'm far from an expert on Gaussian process anyway. But the fact is, this is a leading method used in deep learning. So it's you know, and this was in an AI, you know, pretty prestigious conference. So they wouldn't have been impressed if we compared it against something that nobody knew about. Yeah.
I think just for this sort of application, they don't use, it's a zero mean GP. And this zero mean GP always used in this sort of application.
But because they found that it works well, or?
No, in machine learning, generally the trend is to use zero mean GP. It's in uncertainty quantification, we model mean function. But if you look in machine learning applications, they generally use zero.
Mm-hmm. Okay. Let's see what I want to say here. So, so this was very good results for that on this kind of problem. And so the graphs above show that our RBF algorithm, which is deterministic, that was the big difference between it and the Gaussian process one, which has no expected improvement, outperformed the other algorithms significantly, including the Gaussian process one. And also in other papers we find that below about a dimension of 7, our algorithm performs statistically about the same, I mean, as a Gaussian process. But if the dimension is 10 or greater, we find that it usually significantly outperforms Gaussian process. So this is a project that I'm currently undergoing, which is to try to really address this issue, because it's very frustrating to me. We've been publishing on these deterministic surrogates for years and years, and yet people are all using Gaussian process models and they're not using our surrogates. So I want to try to do a more fair comparison of the two. And so if you guys have suggestions for me about how I should do this, I would appreciate that. Maybe not necessarily at the moment because we're time limited, but I'll be at the conference so you can talk to me. But this is a comparison, just one of the, we're doing lots and lots of tests right now. This is on just a summary with 7 test functions. There's a method by Moore and Wild which enables you to put together the results for over multiple test problems to get sort of a summary result. And highest is best, and this is the number of evaluations that you do. And again, because these are expensive, we really care what happens way back in here. We'd like to do very few evaluations. And then what do these numbers mean? So the GPEI, which is these two right here, is a Gaussian process plus expected improvement with a squared exponential. STA means it's a stationary covariance. NONS is a non-stationary variance, this one. And then for our methods, which are these 3 here, they all say dicores. And C means you have a cubic spline, or a cubic rather, kernel. T is a thin plate, and G is a squared exponential. So this squared exponential is more similar to these other two in that they all have the same kind of kernel. And remember that in our case, when it says dicores, it means we're using the mean of the surface. We're not using any covariance estimates. And so you see that on these 7 problems, we do much better. These are so in this case, the cubic and the thin plate spline do equivalently well. and that the two, I mean, I always thought maybe the problem with GP was that the covariance wasn't stationary, but even when we use an unstationary method, you see it does do better eventually, but it takes it a long time to get going. So these are doing significantly worse. And then also what's notable is you look at these have the same, these both have, this has the same squared exponential kernel, but it's not using the expected improvement. This is using our method, so it's using a mean of the Gaussian process surface, but it's using our method to pick the next point, which is not an expected improvement approach. And you see it does much better than these do. So the differences in our methods are not just the surrogate, they also have to do with how we pick the next point, yeah? Which I'm going to explain how we do that.
Excuse me, in your GP with...
Can you speak up a little bit?
Yes. In GP with expected improvement and with squared exponential Gaussian process,
Yeah.
have you considered the effect of nugget in the optimization? Because I'm sure with this smooth kernel, sometimes the effect of nugget is huge.
That's something we'd have to talk about afterwards. I mean, I'm not blowing you off. I just don't really know enough to to discuss it. I'd like to have you explain to me because that's exactly the kind of comments I'd like to find out more about. Okay, so yeah, so just pointing out here that this has the same kernel, but it's doing much better. So the question is, what do you guys use expected improvement? What do we use? So what's the difference in selecting the expensive points for evaluation? Because that's a really expensive, with these expensive functions, it may be a 4-hour simulation. It's really important where you pick that next point. So GPEI tries to find the point in the domain where expected improvement will be maximized. People calculate the expected improvement, and then they use either genetic algorithm or, at least in the machine learning area, they just generate a lot of random points, and then we'll do a selection to pick the one that's the best. But they're always trying to basing it on maximizing the expected improvement. And it's a very elegant idea. I remember when I first read the ego paper, I just thought, oh, I wish I'd read that paper. I wish I'd written that paper. You know, it was just such an elegant idea that you have this surrogate, you know there's an uncertainty, and you're going to use the uncertainty in the surrogate to help you in your search. But numerically, I don't think it works so well once the dimension gets higher. So we have a different approach, but we're still trying to do the same thing, which is to balance exploitation, which means the desire to go into less explored regions, and with exploration, that's exploration, and then the exploitation, which is the desire to go after the best values. So EI is trying to do that. We also have a method that tries to do that, but does it much differently. So we're trying to illustrate it for a two-dimensional problem. So I'll show you a two-dimensional grid. Of course, we're doing that in much higher dimensions than that. You can call it a weighted candidate approach. First appeared in an article in Forms 2000, and that's also where the theorem appeared that showed that the method converges almost surely. So the term dicores is actually an additional method that we developed in 2013, which builds on top of this earlier method here that has to do with the perturbation. So. This is the way it happens. So here's our domain, and like as is done, say, in this machine learning area, they try to find the next point partly by randomly generating candidate points. In the machine learning area, they seem to generate these candidate points uniformly over the space. We don't do that. We instead pick the best value that we have so far. So let's imagine we've done 100 iterations, and the best solution we have so far is this point right here. Then around that point, we generate, so this is that best point, we generate perturbations that are normally distributed, and that's how we get all these points right here. So this is generating what they call candidate points. Then, and this is and we can also sort of do things to control how much you want the normal distribution to perturb. And then we also...
Excuse me, how do you pick the sigma ends? How do you pick the step size sigma n for the normal distribution?
How do we pick the step? We just empirically found the value of 0.2 works quite well. So it's a, you could try to optimize it, but then that's yet another parameter that you have to deal with. So not to say that 0.2 is the best one you could get, but that's been a very robust value. We also do, the later thing is what we don't, if you imagine you have a long thing, you know, you have 20 parameters and you spent 2,000 or 200 evaluations getting to a good point, you don't necessarily want to change all those 20 parameter values at once. It makes sense to be more cautious. So this is also, this approach is that we don't perturb all the parameters at once. There's a certain probability of any parameter being perturbed, and then as the function evaluations go on, that probability is dropping over time. So you are still perturbing some of the, so in this normal perturbation there's some dimensions that don't get changed. And then, so that's about how we generate the candidate points, is what the previous two slides were about. Now, but you could generate the candidate points in a different way, but the crux of our method, and was done at the initially in our first papers, was then we take, so this is the surrogate value, and this is, so remember we're trying to weight exploration versus exploitation. So this is a surrogate value, and so you would like that to be low, you're trying to minimize. And this is distance to previously evaluated points. So we calculate, just as you would with Gaussian process, you have to calculate the distance to previous points. So every one of these points, we calculate the distance to previously evaluated points, and we take the minimum of those. So the measure of how unexplored a region is for a particular point is how close is the nearest other point that's been previously evaluated. So that's what this distance metric is right here. So this is the minimum distance from previously evaluated points and points selected for evaluation in the current iteration. And so you have these two things. There's a surrogate value, which you want to be low, and you have the distance to previously evaluated points, which you want to be high. Actually, there should probably be a minus sign here, so you're getting the same. Oh, there's a minus. Well, yeah, to get what you're trying to get. And then it's weighted, where the sum of these two weights sum to 1. And so you're just taking a weighted average, take all these points, calculate that weighted average. It's something that's done very fast, and then you can sort them based on a certain weighting as to which is the best point to choose. And then we cycle this in different iterations. So the weight here in one iteration might be 0.1, and in the next iteration, which would mean this would be 0.9, and in the next one this might be 0.3, and then this is going to be 0.7, and so forth. So you're varying how much you care about exploration versus exploitation in a systematic way. So that's what cycling means, is weighting, changing these weights. And when we get into doing things in parallel, then what we'll do is maybe in one iteration we'll do this, but we generate points for multiple. If you have 10 processors, you might do 10 different sets of weights to get that. And for example, here's a case, if you had 4 processors, then you could pick 4 of the points based on 4 different weightings of those. So this has, our method has the same goal, which is to find, as expected improvement, which is to find good evaluation points. I'm just pointing out they're expensive, so you would need to be really careful about that. They'll both have a combination of lower surrogate value, and they'll help improve the surrogate by doing exploration in less explored regions. And we're not using any covariance calculations. So this is in, again, these results for that I showed you before. And that's to explain why this did better, but also to explain the difference between this one, which has the same kernel as this one here, and yet it did better. So this must have something to do with our strategy for picking points. Now you can say this is just on 7 test problems. We're doing more test problems than that, and we're doing it also on more dimensions. Yeah?
In this plot, the kernel and the radial basis function have the same scale parameter?
I think so. I ask you later. I'll talk to you later about it. I'll have to look to see. The student's been sending me this stuff, and so I have to look what's in the file. So I'm just asking for advice, and when I'm trying to do these comparisons. So if you have some opinions, I'd be glad to know how to go about doing a fair comparison between these methods. So the following applications focus on the use of the method developed in 2007, and also what was published in some later papers. There are 3 subsurface applications discussed, including bioremediation, groundwater remediation, and carbon sequestration. The method is general and can be used on other applications. For example, the watershed problem we've also used it on. So this is a site called Umatia. It's a Superfund site. It's a 20,000 acre military reservation in Oregon. It had contamination going into the site over decades. Like 85 million gallons of polluted water was discharged, and these are the contaminations, the contaminants. This is an explosive TNT, and this is another contaminant. So both these things are not things you want in your drinking water, and so there's concern about what they're going to do about it. How do you clean it up? So in this particular case, you're talking about pumping water out of certain locations. They have multiple sites of possible wells, and you're trying to pump out water to pump the water up and have it be decontaminated. The question is, how do you pump that water up? Where do you pump it from? And also that you don't want to pump so much that the wells are competing with each other, for example, and you also don't want to have to pay for more pumping than is necessary. So this was a problem that was provided by the Environmental Protection Agency in the United States as a real problem where they wanted us to do optimization. So the underlying model is a partial differential equation model called a ModFlow, very widely used for groundwater, and that's for flow, and then is coupled to MT3D, which does all the descriptions of the contamination. Computations were done on Yellowstone, which is an NSF supercomputer. Now we had to change the algorithm to do this, so we have our initial steps at initial design. You fit the RBF surface, generate candidate points, select the candidate points, and then collect the results and update the algorithm. That's what we did. That's what you do with GP, and that's what we did earlier in serial. But now what we want to do is to do it in parallel. So that, because these are expensive projects, these big models, and so now these steps in here just take seconds to do. So the big thing is that every time you evaluate the expensive model, the simulation model, that you want to do in parallel. So that means when you do the initial design, you want to do it in parallel. These are supposed to be little computers here showing you you're doing it over multiple cores. And then when you're doing once you design at an evaluation point, you want to do it in parallel. So that means you need not one evaluation point, you need as many evaluation points as you have computers. And so, so to do that took an algorithm change to determine the many evaluation points in parallel. So we have more papers on that, so I'm not going to go into that, just to say that it does require a substantial change in the algorithm to figure out how you're going to pick these points in an efficient way. And these are the kind of efficiencies that we got. With 4 processors, we actually get superlinear speed up, and it depends also on how accurate an answer you're trying to get. This would be the most accurate answer, and especially here we get superlinear speed up to 16 processors, and 64 even is still really good. 84% efficiency for 64 processors is a very good result. But after 64, it just died. It went to 168. 168 wasn't any better than, or 128 wasn't any better than 64. We think it was because it had to use 2 nodes, and having the cross the nodes was causing the problem. There's reasons for why you can see why you might get the superlinear speed up, and it's like there's different processes going on that compete with each other. And I think once typical with these any kind of parallelization, it gets to be a point where more processors just doesn't end up being that efficient. But we got up to 64, which is really good. So, well, how do we compare that to other algorithms? So we're trying to compare, in this particular case, we're looking at parallel algorithms. And this was, we compared against Nomad as a well-known method. It actually was originally a local optimization method, but they've made some adaptations in it to try to do global optimization. So that, and that was available in parallel. ASPEC is a very good parallel algorithm, but it's unfortunately a local optimizer. And then parallel GA, everybody kind of knows what that. So there wasn't very much to compare against, but this is what we compared against. So this is wall clock time. This is the all done with 16 cores, and so this is our algorithm. Lowest is best, and this one is the ASPEC one. It's just a local optimizer. So it found down here and found a local optimum and stopped. But notice its local optimum was a lot worse than where we were at that point. And then the genetic algorithm, not surprisingly, is just very slow. It probably might get the answer eventually, but it typically takes thousands of evaluations. So so that showed that this worked quite well. And so we got some superlinear speed up. And so now, so I've been talking, this is a conference on uncertainty quantification, and I've been talking about global optimization, but I did want to say that we've done a lot of work on, mostly in the past, but we have one paper more recently, on a thing that we call SOARs. I'm not at all a statistician, but I went to David Rupert with my ideas for trying to use surrogates for in uncertainty, and so he's a very good statistician, and so I think the statistical parts have been done correctly. We have 4 papers. The first one is, this is the best explanation, but the problems done here are the simplest, and then we had some later ones that dealt with more difficult problems. So what is the method? The method is that you're trying to do uncertainty quantification, and you're trying to do it with a surrogate. And many of you are doing this sort of thing too. But what we do that I think is different from what most people did was that we start off with a global surrogate optimization. So that's why it's important to have a good surrogate optimization, global optimization method to start with. And also, by the way, this is aimed at maximum likelihood functions that are not unimodal. We're not making any assumption about anything being unimodal, for example. So you do surrogate optimization to find the estimated parameter values. So we're trying to do MCMC, and you're trying to estimate the parameter values from that and the distributions on those parameter values. So we simply are trying to maximize the likelihood function or the posterior function, and doing that with global optimization. So that we do a certain number of evaluations in that context. And those are expensive evaluations. Every evaluation, if it's a 4-hour model, every evaluation takes 4 hours. Actually, we didn't do anything that was 4 hours, but we've done things that took certainly many minutes to do per evaluation. Then now you have all these values, and they have a surrogate that's at the end of this search. Use a surrogate to identify high probability regions. Then, once you've got the high probability region, you build a surrogate of the likelihood function. And then you do MCMC on the likelihood surrogate function. So what's different from what a lot of people do is this part right in here. And actually, the time we first published this paper, I'm not sure people were doing much any way of emulation, but I think since then more things have been done. So the vast majority of the computational effort then is in this stage right here. And then you're still searching around in this stage to get regions in the high probability regions. Our results have been required typically at least an order of magnitude less than if you'd done the thing by maximum doing MCMC and using exact evaluations. So it's a picture of what it's doing. So you're using optimization search in this first stage. So you have this orange line is the maximum likelihood function that you don't really know what it looks like, and then you go in and you're doing maybe the optimization search first tries here, and then it tries here, and then it tries here, and so forth. But what it's going to do is it's going to have a lot more points because it's an optimization search. It's going to have a lot more points in this higher probability region area, And so that's the point of the optimization, is to really identify this high probability region. Once you define can identify, now you have a surrogate that can use to identify the high probability region, then you don't do any more optimization. Then in this stage you go in and you zone in that region and take more samples to get more accuracy. So you're trying to get more accuracy up here, and you don't care too much about being accurate way out here. So, so this is the first paper we did in 2008, which was done on a pretty simple model, and you can see that the fits of the posteriors, these are for 4 different parameters, in this case beta 1 to beta 4, and you can see that the fit between our method, which uses these approximations, and using it, if you did the same problem using the exact function, are very close. We've done this with to other models that were more difficult and had the same result, which is that the comparison of the posterior density functions obtained by SORS and obtained from MCMC using the exact function gave essentially the same result, verifying the accuracy of the SORS method. In one case, it took 62,000 evaluations of the exact function to do the regular MCMC. So, I mean, these were difficult problems, and we compared always the exact function versus if we'd done it with these surrogate. And so besides the 2008 paper I mentioned, there's 2 papers in 2012 and 1 in 2011. But some of those papers are old papers, so I thought I should also show you something newer. So this is not a submitted manuscript, but it's an example of an application to something that's really very difficult. So you probably have heard of carbon sequestration as an attempt to try to capture carbon from an industrial process, and you pump it down into the ground. And they pump it down into, typically, there's underground water all over the world. There's underground water, usually saline, so it's not water that you could use for drinking water. And so the idea is you pump the carbon down here, and it'll just stay there for forever, is the hope. Or maybe it eventually, in thousands of years, will become part of the rocks. And so, in particular, and this can be 2,000 feet. So this is a really deep into the ground. And when you're worried about where the plume is, so you're putting all this CO2 here, and it's moving, and you're worried that it may escape. So, for example, if there was a leak, if there's a crack in the rocks, maybe it would escape through these crack in the rocks and go up here. So you need to do some monitoring on the surface level, and even maybe at some, and this might be an aquifer here too. So, for example, if it leaked up here, then it gets into the aquifer, which is not a good thing. So our goal was to try to figure out how to model the plume and to incorporate the uncertainty in that plume for this kind of a situation. So goal is to stochastically describe the spatial distribution of the CO2 plume. Plume just means the spatial concentrations, the distribution that changes in time and in space. And we had a complete PDE model, which is called TUF2, which is developed by the Department of Energy. So this is a serious computational model that simulates migration of the CO2 plume, but it has parameters. We wanted to do SORS and MCMC on those parameters so that we know their distribution. Once you have that distribution, then you could try to do many stochastic realizations to get a statistical distribution of the future. So again, we use this model, and we use both the exact function model versus our method, the SORS. And you see you got a very close fit. This is on one of the parameters, gas saturation. But the difference is we used 1,782 simulators to get this result, and MCMC used 30,000. So this is equivalent to reducing the computation by a factor of 20. So you might say, oh, that's nice, but you have to realize a lot of these problems, it really makes a difference between whether or not you can do uncertainty quantification. If it's really on these big problems, you cannot afford to do the kind of number of evaluations you would need to do just regular MCMC. So it really has a very important practical use. Here's the same problem, just looking at 4 parameters at the same time, and you see they also fit very well. Now, because we could do this cheaply, we could also look at some other things that we hadn't done before, which is now decisions about how you manage this process. So we want to look, for example, at the effect of the number of sensors on the uncertainty. So here's different numbers of sensors, and as you expect, with more sensors you get more accuracy. We see with just one sensor, you can see the distribution is way down here, spread out, but also its mean, or its peak mode, is at a different place than when you had even 5 sensors. 5 sensors does a much better job. So that was an example of how less expensive uncertainty quantification can also be used sort of to evaluate some management alternatives, where if you're going to have to spend 6 months to do just the original uncertainty analysis, you can't then go back in and do all these what-if questions. And this is also looking at the effect on the parameters for other measures as well. So I'm running out of time. So conclusions on carbon sequestration is, in all problems we've addressed, SOARS has reduced the computational effort by at least an order of magnitude. And one time, I think the first problem we worked on, it was like 65 times. Reducing the computational effort by this much means we can address uncertainty analysis for detailed geosciences models for which uncertainty quantification is not possible. For some simulation models, it's possible to do multiple uncertainty analysis to look at issues like the impact of additional monitoring sensors. And there are other extensions possible. Now, the SOARS method, we have a code, but it's in MATLAB, and I'm trying right now to get a Python code developed, but we don't have that yet. But I could give you information on getting the code for MATLAB code if you wanted it. So this is the slide that I put up when I started, which is that using optimization search can increase the efficiency of surrogate-based uncertainty quantification. That's what I just talked about here, where I think that using optimization at the initial point of setting up your surrogate did seem to, in our results, help a lot with efficiency. Secondly is the discussion about deterministic radial basis functions, that in our observation over like about 10 years, it's usually more efficient than Gaussian process models in higher dimensions. And also global optimization and UQ with a deterministic radial basis function can efficiently incorporate very complex, computationally expensive simulation models of real and complex application problems. So, thank you.
More questions?
Well, lots of questions, but I'll stick to something simple. Your weighted score weights together 2 things that are on different scales. How do you handle that? And how do you handle the scaling of the individual dimensions?
I see. It's normalized. I probably didn't explain that, but you kind of take the differences and it's divided by the maximum or something like that. So those 2 things are both have values between 0 and 1. The 2 quantities are between 0 and 1, and then you're weighting which ones of those.
And how do you scale the dimensions? Your input.
We always, we usually have, so we're working on a closed hypercube. And so everything is converted so that everything's between 0 and 1. All variables are between 0 and 1. It's an attempt to, avoid some problems with some numbers being big and some big numbers not being so big.
But your function may vary very differently in different dimensions. So there's a length scale that we use in the kernel, whether it's a Gaussian kernel or your RBF. Mm-hmm. The length scales don't necessarily match up to that scaling of the
Right.
domain. Do you adjust them, or do you just use the domain measure?
In what we're doing, we just use the radial basis function, and we're not adjusting the length scale. And so the results you see are doing it that way. And maybe it could be improved if we did some of those things.
Yeah, go ahead.
Are you doing the calling? Okay.
And just one question. Did you try out when you are comparing Gaussian processes with the RBF deterministic thing? Did you try out the hybrid thing where you take just the Gaussian process mean function and throw away all the uncertainty and use your exploration?
Well, that's what I was saying. As far as I can tell, and we could talk about this later, but as far as I can tell, that's essentially what we have done with that. The one I said it's our RBF, but it has a Gaussian kernel.
No, I mean like, so you are using a cubic RBF thing.
We use a cubic, but
Yeah,
I also
and-
showed you one of the examples I gave was using a Gaussian.
But you
square
it's
explanation.
similar to cubic function covariances in Gaussian process as well.
Oh no, we didn't try using cubic in a Gaussian function. No.
Okay, last one.
So when you look at your weighting thing, you've got the first part, which is your surrogate, which is the mean of the Gaussian process you're fitting, as you pointed out, because you really are fitting a Gaussian process.
I guess so. I mean, I'm not sure about the language so much.
And then the second term, that distance term, that's really a proxy for the variance, because the variance is going to depend on the distance from the points. That's one of the points of the Gaussian process, because it's interpolating. So that distance is actually a proxy for the variance.
I don't know about word proxy.
It's
Because the thing is, the variance is not necessarily accurate on these functions. So to speak about, my view, you guys can tell me differently, but my view is that we're talking about functions that look like this. And so you don't have a constant covariance over that whole space. And so the variance is not itself something given. We're instead using the distance. You're right, we use that in place of EI. We didn't want to use EI, so we're trying to do what EI does, which is to try to encourage some movement into areas that are unexplored. So instead of using EI, we use this distance measure, saying that our measure of how unexplored it was going to be was how far away is it from a previously evaluated point.
But that is a measure of that variance.
Okay. But I think you'd have to. I'd like to talk to you afterwards about it to get a better understanding of why. To me, it's still not the covariance matrix that you're calculating, right?
It's the marginal variance. It's a proxy. It's not exactly the marginal variance, but it's a proxy for the marginal variance. And that's why it works.
Well, yeah. I mean, okay. It's an attempt to prove that you're getting into these unexplored regions, and we both agree that you have to have some way of pushing the search into some of those regions, but in a sensible way.
It sounds like a perfect discussion for you two to have during the coffee break, which I am now going to force. So I'd like to thank Christine Wall.
Thank you very much.